Welcome back to Math 31. This is the lesson on the factor theorem and division, so it fits in nicely with the overall factoring review that we have been doing lately. So the factor theorem, which you might recall from Math 20 or Math 10, goes basically like this. X minus b is a factor of f at x if and only if, which is what that means, f at b is equal to 0. So really what it means is that when you substitute in a number that's a potential factor of a polynomial, you look for it to be equal to 0. If it is, then you've got a factor. Then you know that that is a factor. And generally it's used to help factor difficult or higher degree polynomials, so cubics and fourth degrees and things like that. So if you had a question like this, is x minus 1 a factor of f at x equal x cubed minus 6x squared plus 11x minus 6? Well, the conventional way to answer this question is to work out f at 1. Now remember, this is your factor, so the root that we'd be testing would be x equal 1. You set it equal to 0. So 1 cubed minus 6 times 1 squared plus 11 times 1 minus 6. You work all that out, you will get 0. So f at 1 is equal to 0. So therefore x equal 1 is a root, and x minus 1 is a factor. I said root, but it could also be called a 0, or it could also be called an x-intercept of the polynomial. Now, that'll only get you so far, because if you are ultimately trying to break down a higher degree, higher ordered polynomial, you don't want to be just randomly picking numbers, substituting them in, and seeing if you get 0. It's not very efficient. So we turn to what is called the integral root theorem. Again, a review topic. You might remember this from an earlier day. An integral root theorem goes like this. For any polynomial function, and I've given you a rough definition of a polynomial function by saying that the exponents are going to be natural numbers. In fact, they can be whole numbers too, but in this case, the way I've got it expressed, I'm keeping it as natural numbers, meaning 1, 2, 3, 4, 5, 6, 7. No fractions, no decimals, no negatives. And if you want to determine what the roots are, or where to start, you always start with the constant term, the d. So everything is going to be a potential, every potential root will be a factor of d, whatever that number is. So it means that you can be a little more efficient when you're breaking these down. And once you decide you're going to break down the polynomial, that's when we turn to division. So we'll be doing that very, very soon. Like right now. So if you're given this polynomial, now this one will look familiar because it's the one that we just did. But even if we didn't have that information, we would be able to start someplace because we know the potential integral roots will be factors of 6. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So you don't waste your time on 4, on 5, or 1/7 or anything like that. Now we do know from earlier that x minus 1 is a factor. So we don't need to go back to that. But I'm going to do long division, and I'm going to break this one down fully. So I take the factor that we know, which is x minus 1, and I divide it like this. X minus 1 divided into the polynomial x cubed minus 6x squared plus 11x minus 6. And with long division and synthetic, which we're going to get onto soon, we always have to make sure that all the terms are accounted for. If you're missing an x squared or any x term, you have to put it in with a 0. And that matters a bit, and I actually don't think I took in an example that requires that, so I'm going to remind you of that. The process otherwise, we take a look at what they call the divisor, which is the number you're dividing by. And then your dividend is the number you're dividing into. And then, critically, the quotient is what we get after we divide. And that's the one that I am most interested in. Because we know that this one should give us a remainder of 0. Simply because we already know that x minus 1 is a factor, so the remainder should be 0. And with the division, you ask yourself, in the divisor, what do you multiply that leading term, the x, by to be equal to x cubed? Answer would be x squared. And then you multiply that x squared by both terms in the divisor, and then write that below. So x squared times x is x cubed. Should always get the same number below. And then x squared times minus 1 is minus x squared. And then we subtract. Now be careful with the subtraction, because x cubed minus x cubed should be 0, but you've got to go negative 6 x squared minus negative 1. So negative 6 minus negative 1 is negative 6 plus 1. So that's going to give you negative 5x squared. Now a very common method is to change this to be plus and then change the two signs inside of it. And then just add, with the plus sign. And that's okay. Mostly I would recommend caution. Now we keep going, and the divisor of x minus 1 into negative 5x squared plus 11x. X gets multiplied by negative 5x to give you the negative 5x squared. So we should always have that number. And then negative 5x times negative 1 is plus 5x. And once again we subtract. And our subtraction now will eliminate those 5x squared terms. And then 11x minus 5x is 6x. And then we bring down the negative 6. And we're in the final steps now. The divisor term x gets multiplied by 6, positive 6, to be equal to 6x. So that would leave us with 6x minus 6. Now you can see that they're equal. And in fact, when you subtract, you will get a remainder equal to 0, which we did expect. And now that we have the quotient, we can write it out like this. And typically, they'll use q at x for the quotient. And that would be x squared minus 5x plus 6. And then we recognize, hopefully, that this one will factor. It factors into x minus 2. And x minus 3, easy for you to check. And now that we've broken the quotient down, we now know that the polynomial, the original polynomial f at x, will be the product of these three factors. The original one, x minus 1, which we knew worked, and now x minus 2, x minus 3. So the division method made it possible for us to break this cubic one down. You could have tried grouping it, and that wouldn't work. I didn't take the time to do it or try it. So this is what we do. Now the other thing that you can do with this is synthetic division. And synthetic division is helpful because it eliminates the x terms. So you just deal with the coefficients. It also is helpful because we add instead of subtract. So you'll find that keeping track of your signs is a little easier. So if we're going to take x cubed minus 6x squared plus 11x minus 6, we're going to divide by x minus 1. We take these coefficients and we put them into our division statement using a European style of division like this. And the coefficient for x cubed is 1. Minus 6x squared is minus 6, and then positive 11 minus 6. So we take those coefficients, and importantly, we don't divide by x minus 1, we divide by x equal 1. So we always divide by the root. And that's why we end up with all the positives, or the adding. I always put a little dotted line after the last term. Then we carry the 1 down, the number from the dividend, the leading term, and that gives us something to multiply by. So we take the divisor, the x equal 1, and we multiply that 1 by 1, and we put the product up there below the negative 6. So 1 times 1 is 1. And here's the payoff. We add. We don't have to subtract anymore. So negative 6 plus 1 is negative 5. And then we continue to multiply by the divisor by that. 1 times negative 5 is negative 5. We add again. 11 plus negative 5 is 6. 1 times 6 is 6. So the remainder is equal to 0, which we expected. And I'm not going to spend a lot of time finishing this one off because we know it works. But now we convert it back into polynomials. We reinsert the x's. So it's 1x squared minus 5x plus 6. So we're 1 degree down. We started with a cubic. We divided by the linear x equal 1, and that would leave you with x squared. And therefore, f at x, going right to the answer, is equal to x minus 1 times x minus 2 times x minus 3. Now, moving on to another example, let's try this, and basically it's going to be freestyle, so I'm going to actually use synthetic division for all these ones. And I'm going to cheat a little bit too, because I'm going to use my calculator to help me to see what works. So with this one, the potential roots, and by the way, stop me at any time and go through it yourself. They must be factors of 12. So plus or minus 1, plus or minus 2. So the signs we don't know. Plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. And at most, 3 of them would work because it is a cubic. Now, I normally recommend you start with 1 or negative 1. And that would be okay in this case too. But I'm actually going to graph this one and see what works. And if you do graph it by trying to see what the x-intercepts are, don't just do a visual inspection. It might occur to you, that negative 1 works. So by inspection of graph, x equal negative 1 is a root. Now, I wouldn't worry too much about this, the fact that you're using your calculator to help you. It's true that you may not always be able to do that, and you have to be able to do the algebra. But this is a time-saving thing, and it's not a big deal. I know that everybody can divide, so I'm doing it the quickest way that I can, just so we don't have to spend a lot of time trying 1, 2, 3. So let's see. X equal negative 1 can now be divided into these coefficients of 2, x cubed, minus 3x squared, minus 17x, and then minus 12. And I will again put the little dotted line before the negative 12. Carry the 2 down. And then negative 1 times 2 is negative 2. And then add. Negative 3 plus negative 2 is negative 5. Then negative 1 times negative 5 is positive 5. Negative 17 plus 5 is negative 12. And then negative 1 times negative 12 is positive 12. Remainder is equal to 0. So it gave us that remainder of 0, and it worked. So we do know that x equal negative 1 will produce a factor. If you bring the 1 over, x plus 1 is a factor. It also means that our quotient is quadratic, 1 degree down. So 2x squared minus 5x minus 12. And now we factor this, or we try to. Not everything factors, but let's see what we can do. So we break the 2x squared into 2x and x. 12 could be 3 and 4, could be 2 and 6. I'm going to try this. And maybe a negative and then a positive. Check to see. I'm not going to labor over the factoring for too long. But this does appear to work. 2x plus 3, if you get the middle terms added up, you should be in business. So therefore, this original polynomial p at x is going to break down into x plus 1, 2x plus 3, and x minus 4. Now, the very last one, I don't think anything strange happens here. And again, I really recommend pause me and have a look and try it yourself and see if you can get anything to work with this. Now, you may want to graph this one just to get a look to see what works. X cubed minus x squared minus 9x minus 12. And if you can, you get a peek at anything that works. They will have to be factors of 12. And I am cheating because I think that 4 works. So by inspection, x equal 4 is a root. Now if you didn't do it like that, you try 1, you try -1, etc., and you'd eventually get to your answer. So I will try x equal 4, put it into this expression. We're all there. Like we're not missing any x terms, so we can go 1, -1, -9, -12. Carry the 1 down. 4 times 1 is 4. -1 plus 4 is 3. 4 times 3 is 12. -9 plus 12 is 3. 4 times 3 is 12. So we get that remainder of 0. It means that x equal 4 is a root, so therefore the factor would be x minus 4. Quotient is equal to x squared plus 3x plus 3. Now, in order to factor this, we would look for two numbers that multiply to be 3, that add up to be 3. And in fact, and they're both positive, it won't factor. So the only thing that is noteworthy about this question is that we only can take one linear factor out of it. That's x minus 4. And we write the quadratic factors x squared plus 3x plus 3. Nothing more we can do with it. And the graph, of course, would have given as much information, because if you take a look at the graph, you'll see it only has one x-intercept. So it means that you get a non-factorable. In fact, this one would produce non-real roots, that quadratic. So that'll give you something to play around with. Everything is freestyle with these. It could be long division or synthetic division. But you've got to be able to have the means to break down cubics, fourth degrees, or what have you. So that's it for this lesson. Thank you for your time.